Screen. Okay, so last class we started talking about spherical coordinates, but we're actually going to skip the majority of that section and until we get to integration where it's used more, and now start with vector valued functions and start doing some actual calculus. We probably won't get to any calculus today, but this is the beginning of that. So a vector valued function is a curve in R3. So we have seen lines, and we saw that the equation for a line is okay, let me refresh this. So we saw that the equation for a line is R of t. Okay, R of t is equal to R0 plus TV. And we also saw how this can be written in terms of something in each coordinate. Let's say x0 plus tx. Sorry, let's go with TV1, y0 plus TV2, and z0 plus TV3. So every coordinate has some value, and this we saw traces out a curve. Now we would like to talk about general curves. So that would be some function r of t, and you again have an x of t, a y of t, and a z of t. So for every point in time, you're told exactly where you are in your 3 dimensions. So this is a good picture illustrating that. Here's your curve. The pink line is your curve. And for any given time, t1, t2, t3, you have a vector, right? Because for some given time, let's say for t, r of t1, you get some actual value, x of t1, y of t1, and z of t1, which tells you where you are in your 3-dimensional space. So it's some vector. But as you allow t to vary, you get this curve. So again, a good picture for this is you are in 3 dimensions. Okay. You're in 3 dimensions, x, y, and z. And you have some curve. So let's say this is your curve. And this curve is given in the form r of t is equal to xt, yt, and z of t. And so for any given time, let's say for r of t1, you might have a vector starting at the origin, of course, and going to, let's say, this point over here. So this is the point r of t1. And again, it's a vector, because if you plug in t1 here, you get a vector. For r of t2, you might get a point here, r of t2, and so on. Okay, so it gives you some curve. So what are examples? So one example is, let's say, this over here, R of t. And in general, we will see that the goal will not be to, yeah. Okay, the general goal will not necessarily be to graph this R of t, though in some cases we will want to graph it. It will be to, let's say, do some calculus on it. But you can have R of t is equal over here to t squared e to the t and 4 minus 7t. So that would be this example over here. But you can really almost do anything you want. R of t is equal to, let's say, t, 2t, and t squared, and so on and so forth. And this just tells you, plug in your t, you'll get a vector. Plug in another t, you'll get a different vector. If you just plug in all your t's, you get some curve. And like we said, we've seen this for lines. So here's a line. It's the simplest version of this. Okay, so one of these curves that they would want you to be able to graph is this one right over here. R of t is equal to cosine t sine of t1. So R of t is equal to cosine of t, sine of t, and 1. So when you see something like this, your intuition should try to be what's happening in each dimension. So in your z dimension, you're just going up by 1. So that's pretty straightforward. Here's your x, here's your y, and here is your z. And in your z direction, you just go up by 1. So you're here. The question is now that you're up in the z direction, what's happening in the x, y direction? So we know that cosine of t squared plus sine of t squared is equal to 1. And that's going to tell you that this curve is a circle. You go up by 1 and you get some circle. So because of that, you know that x squared, because this is your x over here, x of t. So x squared, or let's say x of t squared, plus y of t squared is equal to 1, right? For these dimensions, because this over here is cosine and this is sine. So, but if you know that when you take your x and your y and you square both of them and you get 1, if you know that that's what happens, then you know that you have a circle. So you get some circle over here with radius 1. And that's the curve that this traces out. So as soon as you see sines and cosines, you should immediately think, oh, this might look something like a circle. And we'll see different examples of this, but this is the simpler case. And so that's this picture over here. So now for any t, because the x and the y of this equation satisfy this x squared plus y squared is equal to 1, because that happens, because again, cosine squared plus sine squared is equal to 1. So because that you satisfy that equation, you must be on a circle, and you're at height 1. So that's this circle over here. And that's the curve that this R of t traces out. Any question? Okay. But in general, these curves can be pretty chaotic. Now over here, they give you an R of t with 4 dimensions. Oh, is it 4 dimensions? 1, 2, 3. No. Oh, viewpoints. Got it. Okay. Not 3 dimensions. And they just tell you that this is how the curve looks. So it looks something like this. Obviously, you will not be expected to intuit anything like this or draw anything like this. It's just useful to see different curves that can be made using this, notation. Okay, so the next type of curve that they would want you to be able to draw and picture is a helix. So that's given, and they're telling you, okay, find the curve given by R of t is equal to negative sine of t, cosine of t, and t. So if you remember, the last problem that we did had a 1 here. But now instead of a 1, we're just going to, and the sine and the cosine were in different places, and there wasn't a negative for the sine. That's basically the main difference. But again, you get, because that this is your x of t, and this is your y of t, that your x and y, so you get x of t squared plus y of t squared is equal to 1, right? Because you have negative sine of t squared plus cosine of t squared is equal to 1. So that's what you're getting in your y, your x and your y coordinates. And the question is then what's happening in the z coordinate? And the answer is, well, as time goes positive, it goes up. And as time goes negative, it goes down. So we can imagine, if we graph this, that instead of getting a circle the way we did before, we now get a helix. So now, and of course it will go in the negative as t goes negative. So again, we get this circle. So same thing as before. In the x and y dimension, so here's your x, here's your y, and here's your z. And if I projected this entire thing down into the x, y dimension, so here's x and here's y, I would just get a circle. So that's how this thing would look from above. But instead of getting the circle, I get a helix because that I have in the z direction, I have time. And so as time is positive, you go up in your z direction. And as it's negative, you go down. Any questions? Okay. So here they draw this helix. I would now recommend picturing the projections into the YZ or the XZ direction for too much intuition. I mean, you're getting cosine and sine. A better way of looking at this is just by looking at the projection into the XY plane and then thinking about what t does. So I think that that's the more appropriate way of thinking about this. Okay, so we know how to draw a circle in 3 dimensions. We know how to draw a helix. Another thing that you can be asked is if there are 2 surfaces, so here are the surfaces, and they tell us one of them is x squared plus y squared is equal to 4, and we know that's a cylinder. So that's this cylinder over here. And the other one is this saddle, which is given over here. And they ask us to find the intersection of these 2 surfaces. So they put the cylinder inside of the saddle, and then they're asking us, okay, can you tell us what is this right here? How to get this R of t? So let me write this x squared minus y squared is equal to z minus 1, and x squared plus y squared is equal to 4. Okay, there are two ways that we can use to solve this problem. The first one is by substituting for y over here. So by this equation, we get y is equal to plus or minus the square root of 4 minus x squared. And so then putting that in this equation over here, we're going to get x squared minus, and then it doesn't matter if the y is plus or minus, you're squaring it. So you get minus 4 minus x squared is equal to z minus 1. So now we get z is going to be equal to 2x squared minus 4 plus 1, so plus 3. Sorry. Minus 3. Okay, so now when we write our R of t, we can say, let's imagine that my x is t. So let's take x is equal to t. So you put in one of these a parameter, your t. So that would be t here. If your x is t, can anyone tell me what y is going to be? Yes. Yeah. So square root of 4 minus t squared. Right? You just plug your t into this x over here. And then your z is going to be 2t squared minus 3. Just plug your x into there. Okay, and that's what we get here. Let me see something. So they are saying, they said somewhere that y is positive. Where y is positive. So that's why you don't get, so you only get the positive, you don't get the negative. Okay, any questions? So it's actually fairly straightforward what you end up doing, right? You just try to solve for one of your variables. So that's what we did here with the y. You then try to solve for a second one. As long as you can get y in terms of x and z in terms of x, you just take your x to be t. So you just plug in for x, t. So for x, you put in t. In your y, you put in t over here. And in your z, you put in t over here. Yeah? Any questions? Okay. Okay, another way of doing this is by looking at these equations. So you get x squared plus y squared is equal to 4. And x squared minus y squared, x squared minus y squared is equal to z minus 1. So what can we say about x squared? Well, we can say that if I take my x to be 2 cosine of theta, and I take my y to be 2 sine of theta, then this x and this y satisfy this equation over here, right? I just plug them in and I get 4 in the end. So this is fine. I can take this for my x and my y. But once I have that, what can I do in order to find my z? I can just plug my x and my y into here. So I'm going to get that z is equal to 2 cosine of theta squared minus 2 sine theta squared plus 1. Okay, now let's just replace theta by t so that it fits the picture that we want it to fit. So we can say, okay, r of t is equal, in the x direction, I have 2 cosine of theta of t. In the y direction, I get 2 sine of t. And in the z direction, I get 2 cosine of theta squared minus 2 sine of theta squared plus 1. So that's now what my r of t is. So we get 2 different r's of t, but in fact, they lead to the same curve. So the first one was here. This is the first parameterization that we found. And the second one is here. But in fact, they give you the same curve. And the curve that they're giving you is okay, whatever. The curve that they're giving you is this curve over here. Okay, so that's your r of t now. Any questions about this? Okay.
Oh, why did it say t equals x?
So in the first one, we see that we can find an equation that compares y and x. And we find an equation that compares z and x. So, but listen, you can write r of x if you wanted to. It's just like the formality. We want r of t. We just want a t there. But you can say r of x should be equal to x, the square root of 4 minus x squared, and 2x squared minus 3. And this is also it's a curve, same exact curve as you vary x. But x is really a dimension. So what do you mean by varying x? You're now like having x twice over here, once in your dimension and once as a parameter in your curve. So, okay, instead we say, well, I want this all in terms of t. Let's just take x is equal to t.
Thank you.
All right, any other questions? Here. Any other questions? So,
What is like the cosine and sine using, but the v is
so like same thing. We just want it in terms of t. You can write r of theta and just do everything in sorry. That I agree with. Right? That makes sense. Although if you put in the side t is equal to theta, it actually doesn't matter. But any other questions? Okay. So they say parameterize the circle of radius 3 with center over here, located in either in the plane parallel to the xy plane or parallel to the xz plane. Okay, so what about the xy plane with this center? So what we're looking for, if this is my coordinate axis X, Y, and Z, we want to go to the point 268. So 268. So let's say it's okay, 2, 6. Let's say it's this point over here. So this is my center P. And we want a circle that's parallel to the XY plane. So the first thing we can try to do is just find this circle. So we can say that this circle should have the form, because we want it in the XY plane, it should have the form cosine of t, sine of t, and let's say in the z direction 0. So this is a circle just in the XY plane. So that's a circle that is something like this, and it has radius 1, and we're looking for a circle of radius 3. So, but this circle is right over here, just in the XY plane. The z dimension is 0, right? If you take your x squared plus your y squared, you get 1. So it's a circle with radius 1. In order to get it to have radius 3, we just put a 3 here and a 3 there. Okay, now it has radius 3. But now we want it at this point P, which I did not write, I guess, which is the point 268, 268. So this is the point 268. Well, we can just add it over here. So let's go plus the point 268. So what does this do? It says, okay, take a vector from here to this point, the P point, 268, that's your first vector, and then add to it the vectors that form this circle. Okay, and this is your R of T. So that solves the first problem. The second problem says we want same circle, but now parallel to the XZ plane. So for the XZ plane, we can go here. We can say, let's begin by having 0 in the Y dimension and putting a cosine of T in the X direction and a sine of T in the Z direction. So now this is a circle with radius 1. Centered at 0 in the XZ plane, right? Again, because if you take x squared plus z squared, you get 1. Well, again, in order to change the radius, we put a 3 here and we put a 3 here. So that changes our radius. And then we just add the same point as before, 2, 6, 8. And now that's my R of T. Any questions? Okay, and that's what they did over here. So this is your R1, and this is your R2. And a picture, here's a picture of both of these. So here is your first one. The circle is parallel to the XY plane and is at the point 268. And here the circle is parallel to the XZ plane. And again, has the center 268. So in summary, we learned that we can not only write curves for lines, but for other things too, circles, helixes, intersections of surfaces. Maybe that one is the trickiest of them. And okay, that's basically the section. Any questions? Okay. So So now that we have curves in 3 dimensions, we can start doing some calculus on these curves. And the first notion that we need before we start doing calculus in general is that of a limit. So if you have some function R of t, so vector valued function R of t, and you take its limit, as t goes to a, let's say. So you take the limit as t goes to a of R of t, and you take the magnitude of R of t minus, let's say, some vector u. So again, this R of t is some curve. So here's your curve. And we can say, let's say that this is your u right over here. This is your vector u. And as I take t closer and closer to a, let's say my vector is getting closer and closer to u. Then we say that the limit as t goes to a of R of t is equal to this vector u. Okay, and that's this definition over here. So a very intuitive definition for the limit, same thing that we've seen in Calc 1. You take the limit, and if as you approach your vector, your distance goes to 0, which is given here, then we just say your limit is that u. An important fact about the limits of vector valued functions is that if you're asked to take the limit as t goes to t0 of R of t, that's the same as taking the limit in each component. So limit as t goes to t0 of the xt component, limit as t goes to 0 of the yt component, and the limit as t goes to t0 to t0 of the zt component. Okay, and it intuitively makes sense. If each one of your components is approaching this vector u, then your R of t should be approaching that vector too. So instead of, so how do we actually find limits for vector valued functions? Well, we take the limit of each component individually, and we know how to do that from Calc 1. And that's this over here. So the limit as t goes to t0 of RT is the one for each component. So they ask us to calculate this limit over here. So the limit as t goes to 3 of R of t where R of t is equal to t squared 1 minus t, so t squared 1 minus t, and t to the negative 1. Well, because of this limit, as we approach these points, okay, so let's first write, okay, so this is equal to the limit as t approaches 3 of t squared, the limit as t approaches 3 of 1 minus t, and the limit t approaches 3, and the limit as t approaches 3 of t to the negative 1, right? By the theorem that we just saw. Well, each one of these doesn't have a problem if you just plug in your 3. So we can say, okay, this is the same as 3 squared, 1 minus 3, and 1 over 3. Okay, and that's your limit. Okay, now that we know how to take limits of vector valued functions, we can take derivatives. And the derivative is the same as the derivative for single valued functions, because ultimately this is basically a single valued function. So we can say r prime, and this prime is with respect to t, because that's the only variable that you have, is equal to the limit as h approaches 0 of r of t plus h minus r of t over h. So same exact formula that we've seen in Calc 1. But because the limit can go into every component, what we can in fact do when we want to take the derivative of r of t is we can just take the derivative of each component. So that tells us r prime of t. Well, because we can put this limit into each component, r prime of t is going to be equal to x prime of t, y prime of t, and z prime of t. Okay, so far everything is very similar to Calc 1. So they ask us to calculate some derivatives. So let's say over here, we have what is the derivative of the vector t squared, 3t to the third, and sine of t. Well, that's going to be 2t, 3t squared, and cosine of t. Right? Because we just do the derivative of each component. And you can do this yourselves. And the second derivative is just the second derivative of the first one, which is the second derivative of each component, and the third derivative is third derivative of each component. So they ask us to calculate for r of t is ln of t, t, and t squared. Ln of t, t and t squared, t squared. What is the second derivative at 3? So please take a couple of minutes and do this problem. Yep. Oh, t, yeah. So the first derivative, r prime of t, is going to be 1 over t, 1, and 2t. And then the second derivative is going to be t times the derivative of 1, which is 0, minus 1 times the derivative of t, which is negative 1, over t squared. 0 and 2. So now we plug in our 3, so r double prime 3, negative 1 over 9, 0, and 2. Any questions? Okay. So we have the same rules that we had for Calc 1. The derivative of the sum is the derivative of each one individually. If you multiply by a constant for the whole vector valued function, you can take your constant out. If there is some function f of t, so this is some constant function, like let's say you have r of t is equal to t squared 1 and t, and now f of t is not a vector. Let's say f of t is t squared. So f of t times r of t is going to be, this is t, is going to be equal to t to the 4th, t squared, and t cubed. So that's what that notation means. The f of t is some constant function, the r of t is some vector, you can multiply them. You have the product rule in that case. And of course, you're going to have the chain rule. If you don't have, t over here, but you have g of t, you can just take the chain rule. And this all follows from the single valued case, because that when you take the derivative, you just go into every component individually, and that's what these proofs basically do. So for example, and it's not very important for you to remember these rules, especially if you know the previous ones. When you actually have to do it, you'll just see that, oh, you need to do this rule. Okay, let's do the first one over here. So they say r of t take r of t to be equal to t squared 5t and 1, and f of t to be equal to e to the 3t. So the question was, what is the derivative of f of t, r of t? Well, we know that this is just the derivative of f prime of t, r of t, plus r of t, r prime of t, f of t. And this is equal to k. So the derivative of f of t is 3e to the 3t. And then you just multiply this by t squared, 5t, and 1. Okay, plus the derivative r prime of t is 2t, 5, and 0 times f of t, which is e to the 3t. And so here's your answer. Any questions? Yes. It's okay if you leave it like that. Okay, and I'm not going to do the chain rule one, but it's similar to the chain rule. Okay, we have two more rules, which again don't appear that often. So you don't have to stress memorizing these. One of them is very simple. I mean, they're both very simple. They're just the product rule. So the derivative of the dot product is the derivative of the first one times the dot with the second one, plus the derivative of the plus the first one times, okay, whatever. Derivative first times dotted with second, R1, then dotted with R prime. So it's just the product rule again. Just now, you just remember that you're dealing with vector functions. So the dot product is not multiplication, it's the dot product, right? You can only really multiply if you have a constant function f of t. But if you have two vectors, you have to either take the dot product or the cross product. And again, you just have the product rule. So for both of these, you just have the product rule again. Okay. So yeah, I think we should stop here. Next time, we're going to start talking about the tangent vector to curves. And have a nice weekend.